Alright everyone, let's do part C1. So, for this question, they're asking us, so they've given us a new situation now where there's a magnetic field around the ball. So I might just draw a diagram for us on this side over here. So imagine we've got the ball like this, then we've got a magnetic field coming up like this, call that B, and it's in the Z direction. Okay, and then at some other angle, we're going to have omega. I'm not going to make any assumptions about what direction omega is. I'm just going to imagine it's going around this way. Okay, and we've got charge along the outside of the ball now, so it's going to experience forces and torques. So what I'm just going to do is I'm going to take a random point, or I might not make it so random. Let's pick this point here, so this omega is meant to pass through the middle of the ball. Sorry, so just a sec, I'll make it in line with that. We're going to have to integrate over the surface of this ball in a minute. So I'm just anticipating and I'm setting up that this is my theta direction coming down from the vertical. The radius here that we've got is little r. Vector r is this vector pointing this way. So that's going to be our vector r, and it's going to change direction depending on which part of the ball we're looking at. Alright, let's maybe go from there. So let's just start by writing a few equations. So we normally have like F equals ma, so in this case I'm going to start with our force equation, m, and then I'm just going to call it v dot, going to equal, okay, so we've got like a friction force from the bottom, so in that case that's just going to be, I'll call it friction force, or floor force, I don't mind what you call it, and then we're also going to have a magnetic force, so the magnetic force is given by QV cross B. Alright, so that's a force equation. Now let's do a torque equation. So for a torque equation, I can do... Okay, and tau s that I've got on the end here, this is like the torque that we have due to the fact that we've got charge moving in the magnetic field. So we're going to have to take that magnetic force, and we're going to have to figure out all the points where it's acting on the ball, and we're going to integrate that up to get tau s. So let's give this a go. Just before we do, there's a couple of things that I thought I'd point out. So if we imagine that we've got this little point just here on the diagram, and we're asking where's the velocity, well, we can see that if this ball's rotating this way, that this part of the ball, like our v in this case, is going to be coming out towards us. So v of this part of the ball is coming here. I guess I'll just call that vs. And then we have this relationship here that vs equals omega cross r vector. Okay, so if I have this, let's just deal with the magnetic component of the force. So I'm going to call the magnetic component of the force Fm. Let's imagine I have some small part of that, so dFm. So the magnetic force, let's say due to this little point here, that's going to be dq vs cross b. And if we think about what direction is this going to be on our diagram here, this is kind of interesting. So we've got our b pointing up, and we've got our v out of the page. So when I do that, I get the force is actually in this direction here. That's actually not going to be that interesting for us here. That's just kind of pulling outwards. But if we were to consider another point, like this bit at the top here, so this is also having the velocity come out towards us. In this case, the force is still in this direction here. But the torque, then, if we do r cross f, is going to be coming out towards us. So the torque's actually in the same direction as the velocity at the top here. Now if we were to consider the bottom, what's going on here? Well, now we've got the velocity is going into the page like that. That means that our force is going to be going this direction. But if we consider our torque is still coming out of the page when we do that r cross f, because r is down now. So the torques won't cancel out to zero. We can see the one at the top and the bottom here are summing up positively, and then the ones that are along the equator here are going to be like zero. So anyway, we'll take this into account more formally when we do our integration. We've got our force here. Let's write down an expression for that torque. So our d, surface torque I guess you call it, is equal to the r vector cross dfm, r cross, now we've got our so I'm just going to put the dq on the end for in a minute. So here I've got my v, but I know that my v is like omega cross r, so I can do omega cross r, and then that all has to be crossed by b, which is bz dq. Okay, now what I'm going to do here is we're going to have to simplify this. So we're doing kind of like a 3-vector product here. So I'm just going to call these vectors A. I'm going to call this cross product in the middle here B, and I'm going to call this bit here C. Now, what we're going to do is we're going to use a slightly different version of the triple like cross product rule. So this one is when you have the final 2 terms get multiplied first. Now I see why I needed my bracket, because this R cross all of F. That bracket has to go there, and which vector product you do first is actually important here, so we have to get the order correct. So now, rather than doing A cross B all in brackets cross C, now we're doing A cross B C in brackets. So let's do that. So I'm going to write the rule for you in red down the bottom. Let's just break this down. So if we still do D tau S, then we're going to get, so first thing I'd like to point out is A dot B here is strictly going to be 0 because omega cross R is at right angles to R. So that means the second term is going to go away. So we're just going to have a first term here. And so the first term is A dot C, R dot B, and then we're going to still have our cross product there. So, alright, now I want to integrate this up so I can figure out the total torque. So to do that I have to integrate over the whole area. So that means that tau S is going to be equal to, I'm integrating. So in this case I'm going to do from 2 pi to 0 d phi. Now when you do that you pick up a factor of r sine theta, because the distance d phi that you do going around like the equator, our like longitude coordinate, how far you travel depends on the radius, and it depends on whether you're near the North Pole, South Pole, or near the equator. So then we're also going to integrate over theta, and we've got to go from the top to the bottom. So we're going from pi to 0, and that's d theta. Now just from those two, for theta we also have to take into a factor of r. So just from those two we actually get r sine theta straight up. We've got to integrate essentially over the area. So to get this dq here, essentially it's the area, so this d phi and this d theta multiplied by charge density, I'm going to call sigma. And then of course we've still got our terms from before where we have r dot b and the cross product between omega and r. Now for r dot b here, the angle between r and b is not a constant. It changes with time, but it is equal to the cos of theta. So if you have a look at our diagram over here, b is pointing up, r, the angle here is this cos, so and it's separated by this angle in here. So we can see that these are going to perfectly line up when you have theta equals 0, so that's why we're using cos in this case. So if we've got, now it's just going to be the magnitude of r times the magnitude of b, so I've taken away the vector symbols, cos theta, and then we still have omega cross r. Okay, now let's have a look. What are our constants? Sigma's a constant, r is actually a constant here, like that's just the radius, so that's fine as long as it's not vector r. Sine theta is not a constant, cos theta is not a constant. Omega is actually a constant for this integration, so we can pull that out the front. Okay, and then we can do our integral from there. Okay, so let's pull all those constants out the front, and let's substitute in r into our x, y, z coordinates. Alright, now if I think about what is the r vector here, well it's got an x coordinate, a y coordinate, and a z coordinate. What's the x coordinate given by? Well, I haven't exactly decided to find exactly where azimuthal angle is going to be, or my latitude angle is going to be. I don't really care if we set it to sine or cos, it's all going to cancel out, but what is important is that the magnitude of the x coordinate here is going to depend on sine theta. So let's just call this one cos phi for the x coordinate, which then means that my y coordinate is going to be given by sine theta sine of phi. Alright, I'm just going to change color so I can keep writing over the top of my diagram. That's a y. Plus, in this case, I'm going to have cos theta z. These x and y components are going to go to 0. Let's explain that in two ways. First of all, I'm going to integrate from 0 to 2 pi of cos phi and sine phi independently. That's clearly going to be 0, and anything multiplied by 0 is 0, so they're going to go away. That's a mathematical argument. For an intuitive argument, do you remember how we were trying to figure out what was the direction of the torque? And if we had a look, the force is going outwards when you're on the equator here, and that means F dot r is going to equal 0. So really, I only care about the points like where I have z components of r. The x and y is just going to cancel out because that F cross r is going to be 0 when they're in the same direction. So I don't mind if you want the mathematical or the intuitive method, whatever works for you. But what that does mean now is I can simplify this down a bit. So I'm only dealing with the z coordinate. So let's do that. Okay, now doing the integral over phi is super easy. That's just going to give me a factor of 2 pi. Doing the integral of sine and cos here, not quite as easy, but what I can actually notice here is that sine, or minus sine, is the derivative of cos. So that actually means that if I was to think about the expression, I'll just write it in the middle of the board over here, cos cubed theta, and I was going to take the derivative of that with respect to theta, then I would actually get minus sine phi cos squared phi, and I'd get a factor of 3 at the front. So I can kind of use this in reverse to be able to integrate this thing here. So what that means is I'm going to get my, so from my phi's I get my factor of 2 pi, r cubed sigma b omega cross, in this case, sorry I dropped my z. This is all in the z direction. Omega cross z. Alright, and then I have minus 1 over 3 cos cubed theta, and I have to evaluate that at pi and 0. Now when I do this, cos of pi is minus 1, and cos of 0 is 1, so that means that I'm going to essentially get a factor of minus 2. So I do minus 1, and I get a factor of minus 2. So if I put that all together, I already had 2 pi, now I'm multiplying by 2, I'm cancelling out my minus that I've got there, so that means I've got 4 pi, okay, and then this is all going to be divided by 3, then I've got r cubed b, and then I've got omega cross z. Okay, now this is looking like it's starting to get pretty close. However, what I haven't done now is I haven't taken into account that when I did this substitution that you need a factor of r. So there should be like an r here, and an r in front of that. And so that means that I should have actually r to the power of 4 here, and r to the power of 4 here. Apologies for the mistake. And then notice, because I had like sigma as my charge density, but the total charge, which I guess I'll just call Q, is going to be equal to the charge density multiplied by the surface area of the sphere, which is 4 pi r squared. So in this particular case, I can just like make that substitution back for Q to get my answer of Q r squared sigma b omega cross z. Okay, now that I've found that tau s, I've actually got everything they asked for in the question. We've got our Newton's second law at the top, then we've got our expression for the torque, and then we've managed to find the torque due to spinning around its axis in the magnetic field. So let's move on to part C2. Okay, so for C2, I've included the question here, but if you have a look, I've also included the first half of C3. The reason is because in C2 they tell you that they want the acceleration of the ball in terms of these variables here, but then if you have a look at C3, they're actually assuming that you've gone further than that and gotten rid of your omega values, otherwise you couldn't have it in this form here. So that way, because we've got that C3 there, we actually know what we're aiming for. They're not happy for us to have our variable in terms of omega. Okay, and that just is letting us know what we need to do. Okay, so they're kind of nice that they are telling us to use the results of C1, so from that we've got our like force formula, which we can actually rearrange to get the friction force. Alright, then we also have our torque law, which is... Okay, and then what we haven't considered is we actually also have our no-slip conditions as well. So let's just have a look at those. So the first no-slip condition can just be for the velocity. So we have... Okay, and then from this, what I can actually do is just rearrange this for omega. To get omega by itself, or omega r by itself, what I'm going to do is take the cross product with z, so take a cross product of everything with z. Then I'm going to have my nice trick where if I have like z cross something, then I'm going to have those z hats cancel out, which leaves me with... Okay, then I also need to take the acceleration no-slip condition. And then I can actually now do my same trick where I take the cross product of everything with r, and that means that I'm going to get... Sorry, I just missed a dot on my torque equation there. And then I'm just going to rearrange that again to get... Okay, so first step, I'm going to take this and substitute into my torque equation, which will give me... And I'm going to substitute in for F. Okay, and if I take stock of this, this is pretty good. All we've got to do is a little bit more rearrangement and then we'll get there. So the next thing I'm going to do is just going to take the cross product of everything with r z hat. that's going to get rid of some of these z terms on my v dot terms, and it's also going to mean that I can just get rid of this r and that pesky fraction there. And when I do that, I'm going to get, so let's just bring this other v dot term to the other side. Sorry guys, I just realized that there is an error here. I've done this here, this r cross f, but r, this is for the friction force, so rather than it being an r vector like that, it should actually be a scalar r multiplied by z hat. Apologies, so that means that this r is actually, and that's why my I can do this trick to get my v dots, because when I do this cross product here, this z cross v cross z, that's going to cancel out my z's and I'm just going to get my v. Alright, and I had to bring this I omega v term to the other side, so that's minus, and now I'm going to have plus qr squared from this term here, and that'll be v cross b. And sorry, I took the triple product, so that z's gone away. Now, for this part here, I want to get rid of this omega, but luckily I've got this expression that I can use here. So if I substitute that in, then I'm actually going to lose the r, the factor of r that I'm multiplying up. But what that means is that I should get the following instead. And that's all crossed with z. And that's all crossed with b, which is in the z direction. And that's all going to be crossed with z. Alright, so let's just play with this last term here, because we've got a lot of cross products to get rid of. So if we first look at this v term, so we're essentially doing v cross z and then crossed with z. So that means that we're just going to get this factor of b as a constant, and we're going to get a vector pointing in the direction of v, and then we still have to take the cross product with that z. But that's okay, we can deal with that. Now for this other one, we've got r, we're crossing with z first, then we're crossing with z again. So that's going to be nice and simple, we're just going to be left with that factor of r. So let's write it out. Oops, and I forgot to cross this one with z, apologies. Notice that I pick that minus sign up when I do my triple product rule, and so that's why this minus has become a plus here. Alright, then I can notice that this term here, b q r squared v cross z, actually matches the qb r squared over 3 v cross z. So I can just add those terms together, which is nice, which means that I'll be left with, and this one also picks up a minus sign from the triple product. Okay, and if we have a look at our equation, that essentially matches the form that they've got for us at the top here. The only difference is that we could just move all the terms to one side, so that way we get equals to 0. And so if we do that, what that means is that we're going to have, in this particular case, that beta is going to be equal to, and gamma is going to be, okay, and that's C2 done, so now we're all ready to start doing C3. Okay, so I've just included the second half of B3 on the screen here because we've actually already done the first part. And so I've just got our constants beta and gamma on the right hand side of the screen here. It so happens that we won't be using those for a while. But what we do need to do is actually take the differential equations, so they're of this form, and then we need to convert these to polar coordinates. And so they've given us this transform here that we can use to convert from x and y into rho and beta. What we do need to do though to be able to do that is figure out what x dot and y dot are. So let's do that now. So let's start with doing x dot. So all we're going to have to do here is just differentiate, and we're going to use the product rule, and we're going to get, I'm not going to show the t dependence here. So that's our first term. Then for the second term we have to use the chain rule. Okay, now let's do y. It's very similar. Okay, and I'm just putting some brackets there so that way we know what's inside the sign and what's not. Okay, now it's going to be harder, but we just have to do the same thing again to get x double dot and y double dot. So let's do that. Okay, so that's from taking the derivative of rho for the first term. Now we also have to take the derivative of that cos, so we're going to get... Now, when I go to take the derivative of this next part of x, see how it's got rho sine eta, then eta dot. So this rho term, when I take the derivative of that, I'm actually going to get back the expression I've just written down. So I'm going to get 2 of those. So I'll just put 2 there. Okay, so then I can keep the rho constant and then take the derivative of the sine term, in which case I'm going to get, so in this case I pick up an extra factor of eta dot, and then now because it's actually got this eta dot on the end, I also have to take the derivative of that and hold the rho and the sine constant. So that means I'm going to get like that. Now you can do the same thing for y. No, this is actually the same as above. I just put the eta dot in front rather than behind. Great. So now we've got that, we just get to substitute back into these formulas here. Now it so happens that if you do this, you actually pretty much get two equivalent formulas, so I'm only going to do it for this first one here. Okay, so let's substitute that in and we're going to get... Okay, so now we've got that, the next step that we need to do is that we need to make an argument that all of these terms are either multiplied by sine of eta or cos of eta. Now we actually need this to hold true, that this entire expression equals 0 for all values of eta. So what that means is the only way that that can be true is if it's true when all the sine terms add up to 0 and all the cos terms add up to 0. That's the only way it can be true in general. So we can actually split this into two separate equations. One where we get all the coefficients in front of cos and they have to sum to 0, and then all of the coefficients in front of sine also have to sum to 0. So that's going to be our two equations. Let's start by doing the cos terms. So the first thing we get is rho double dot, then minus rho eta dot squared, minus gamma rho eta dot plus beta rho, and that's 1, 2, 3, 4. That's all of the terms. So excellent, that has to equal 0. Now what I'm going to do with that one is I'm just going to actually simplify it, or when I say simplify I mean factorize, and so I'm going to put all the rho terms together. Okay, now we're going to do this for sine. So here we've got 3 terms, and because they've all got negative signs, I'm just going to cancel out those negatives in advance, so that means we get... Okay, and that was for sine. Okay, now the next argument that I need to make is I'm going to try and convince you that this term here has to equal 0. Now, the reason why this has to be 0 is it is actually possible that we could start with no angular velocity, or we could actually start with no velocity at all. So in that case, that means that our rho dot would be 0, and we'd have this rho dot eta dot all is 0 if we started with no velocity. But we still need this equation to be true. It has to hold for all circumstances. And in that case, if we had any sort of angular acceleration here that was non-zero and position that was non-zero, then we could actually have that this equation doesn't add to 0. So using that logic, we can actually get rid of this middle term here. And so that means that we can simplify our equation to... Now it's impossible to guarantee that rho dot will actually be 0 here. So in that case, we know that this part here is actually what's going to have to equal 0. And so therefore, we know that... Oh, whoops, I've missed a 2 here. Apologies, there's meant to be a 2 there. Then I can make that gamma over 2 is going to have to equal 0. Alright, so that's one equation. Now if we have a look. Okay, now what they want us to do is they want us to find the form of eta. Now we have a nice property here that we know that the double derivative of eta is 0. So we know that this is equal to 0. And we know that eta dot is equal to minus gamma over 2. So in this case, I guess we kind of know that we're going to have a polynomial in this particular case. So eta is just going to be, so in this case, minus gamma over 2t plus some sort of a constant. The constant's an angle. It's going to be, by the looks of it, the initial angle that we start in the circle. So I guess I'll just call it theta then. So if we just drew a quick little diagram of the scenario, this is the table, and here we've got a y-axis and an x-axis. So if we have a look, the way that they've defined x up the top here means that if theta equals 0, we're pointing in the x direction, so that means that this could be our initial position here. And then if we move around to, let's say, here, then this angle there, that's going to be our theta. And so I guess it makes more sense to call this theta naught. Alright, that's the functional form of eta. Alright, and now the next thing that they want us to do is to express the coefficient beta prime. So if we have a look here, this chunk of equation here, this is like beta prime. It's essentially just like the beta that we have here, except now that we've kind of changed our coordinates, we've managed to eliminate this kind of first derivative term. So that means we pretty much only have a beta term, and because it's the change of coordinates, rather than calling it beta, we're calling it beta prime. So this is going to be our beta prime. So I guess I can just write that out for us. Okay, and then from there we can actually substitute in our relationship up the top here for eta dot, and so that means that we're going to get our beta prime is equal to, okay, so we've now got our expression for beta prime, which is great, and then the last thing they want us to do, write down the condition for where we have different behavior with respect to our row t. So this is all really coming down to this equation here. So I'm just going to rewrite it in terms of beta prime. Okay, so we've got this form of this equation here. Now what we want to do is consider what does this look like for different values of beta. So let's imagine for a minute that beta is positive. Okay, I've just realized I've made a sign error here, because if you have a look, I've got this as a negative beta here. So this should actually, so I've actually defined beta prime as the negative of this term here. I apologize for that. What that means is that this is actually going to be a plus here. Okay, sorry about that error. Let's keep going. So we've got, if beta prime is greater than 0, then if I was to bring this term to the other side, there'd be a minus sign in front of it, so I'll just write that out for us. So, okay, and if you have a look, we've got the equation where we've got double derivative is equal to the negative of the term. So we already know that that's going to be a sinusoidal type function. So in that case, we know that we're going to get like sine and cos type answers, or in the word that we often call that is a harmonic function. So that means if we have beta greater than 0, this is going to be a harmonic function. Alright, now if beta is not negative, beta is positive, then this is clearly just going to be an exponential. So if you were to differentiate the term twice, you get itself plus this constant back. So it would just be the square root of that constant in the top part of your exponential, or in the power of your exponential. So if you have beta smaller than 0, then this is going to be exponential function. And then the interesting case, I guess, is when beta equals 0. In fact, this is probably the least interesting case. So in that case, we're just going to get a polynomial similar to the form that we had for eta up the top here. So now it's going to be the double derivative of O is going to be 0, and that just means that we're going to have a polynomial or a linear function of order, so polynomial degree 1. So I guess that we could just call this linear. Okay, and that's C3. Okay, so let's do C4. So in C4, they give us a range of initial conditions, and then they want us to use our solution from C3, and we're going to use that to find beta and gamma, and then we're going to find the corresponding value for capital omega, which can tell us how fast the table is rotating. First of all, let's have a look at these initial conditions. So they've given us that the initial position, I guess I may as well draw a diagram for this. Okay, then this is x and this is y. Alright, so we're starting at this initial position here, so that's going to be a distance of 1 meter away from the middle. Okay, and then we have velocity. No velocity in the our velocity in the x direction is 1 meter a second. Our velocity in the y direction is minus 1 meters a second. So that means the ball is going to be going this way. The interesting thing to note about that is that means that it's actually going the opposite way to the direction that we assumed that omega was going. So you might remember previously we were saying omega was this way. So in theory now we should actually get a negative value for omega. Let's find out when we get there. So from these initial conditions we can actually know a couple of things straight up. So first of all, if we wanted to know rho, how far away we were from the center at the start, we know that's going to be equal to 1. And we also know that our initial angle, I think I called it theta or theta naught before, but now I'm going to call it eta naught. That's going to be 0 from the diagram here, because we're starting in that x direction. Oh, sorry, I just realized that I drew that arrow in a slightly wrong direction because we have a positive initial velocity. We're actually going out in that direction. So apologies for that mistake there, but if we keep going, so because we have our initial position is in the x direction and our initial velocity has a component in the x direction of 1 meter a second, that means that we also know that the rate at which initially the distance from the center, rho, is increasing is 1 meter a second. Now we can also figure out what our initial eta dot is. This is actually a little bit tricky in my opinion to kind of think about, but the key thing that like helps me realize this is just looking at the definition of x and y. So if we have a look, x of t, okay, and we might recall that we actually took the differential of this before as well, so I'll just quickly write up those differentials again. Okay, now if we substitute in time is equal to 0 and therefore eta is equal to 0, because of this condition that we have here, then I can actually see that first of all, I recover the first equation is true because this last part goes away. But more usefully, this part here, so this sign is going to be 0, that's going to go away. And then I already know that my rho is equal to 1. I know that my y, in this case they tell us, my y dot is minus 1 meter a second. And cos is just going to be equal to 1. So that means that eta is going to have to be to minus 1. Alright, so then when we do that, we can then use, we've got this equation from before, that we had that gamma plus 2 eta naught has to equal 0. So we have that from our differential equation. If you go back to B3, you'll remember I did something where it's like from sine and from cos, we get these two equations. This one came from our sine term once we established that the double derivative had to be 0. So this means that we can then get our gamma. So gamma is going to equal to 2. Now, to get our beta, what we can do is, luckily for us, we only have to examine the simplest case here. So we don't have to worry about the scenarios where beta prime was greater than or less than 0. We only have to worry about the case where beta prime is equal to 0. So in that case, from that condition, get that beta equals minus 1. And we also know that rho double dot is equal to 0. Now, once we have that information, we know that rho started at a value of 1. And we know that rho has a gradient of 1 and no acceleration. So that means we can actually just find the functional form of rho directly here. So in this case, it's just going to be 1 plus t. Now, we can also actually then find an equation for x and y. Because we know what eta is, we have our eta value from before. So before we found that eta was equal to this here, but since then we've actually found what gamma is, and we now know what eta naught is. So eta naught's 0, so that goes away. And we know that gamma is equal to 2, which means that eta is simply minus t. So we can now substitute all of that into our expressions for x and y. Apologies that I didn't write up the y expression before, so I'll just put it up there now. So okay, so if we just substitute in our functions that we've got, so that's this one and this one, into those equations, then we get, and of course the cos of minus t is just equal to the cos of t, so that means we get, and the sine of minus t is equal to minus sine of t, so we get that. Okay, now at this point I'll just point out, because they do this in the solutions, that this row that we've got here is essentially equal to the capital R, the variable that we've been looking at before, or the scalar version of that. So that means that we can quickly verify, I guess this is true, by doing x squared plus y squared. We know is going to equal to capital R squared, but it should also equal to 1 plus t squared, and we can see that that's true. So now what we need to do is, they want us to use these values for beta and gamma that we've found, and we want to use that to figure out capital omega is, and we've already got a bit of an idea that it might be negative because it's the opposite direction to what we thought originally. And then they want us to be able to determine the sign of Q, so is the charge here positive or negative? Alright, so in order to be able to find omega and Q, what I'm first going to do is take our definitions of beta and gamma, so that's the two that we've got at the top here, and I'm going to set them equal to their respective values. So we have, okay, and we actually also know that the moment of inertia of this ball is mr squared over 10. Okay, so let's substitute that in. So first, let's start with our beta term. So if I just add mr squared to my I in this case, I'm just going to get 11 over 10 mr squared. Alright, and I can cancel out my r squared values here. Alright, and then just a little bit of rearranging leaves me with, now let's deal with the gamma term. So from gamma I have, okay, and then once again we can substitute for I, in which case we're going to get, okay, now I'm going to cancel that mr squared on the top and the bottom, so this goes away, I get a factor of m on the bottom, and that r squared goes away. Then I'm also going to multiply the top and bottom of this fraction by 10, which means that I'm going to get 40, and then those 1 over 10s are going to cancel out. And then I'm going to multiply both sides by 11 to get rid of my denominator. And now what I want to do, just to simplify things a little bit, is I'm going to call this A. So that means that this here is just equal to 4a. And so that means I can rewrite my equation on the left hand side here. That's going to be a omega equals minus 11, and this one here is going to be 4a minus omega equals 22. Alright, so from this equation on this side I can get that a is equal to minus 11 over omega, and I can substitute that into my right hand side, so then I get 44 over omega minus 44 over omega minus omega equals 22. Alright, so let's rearrange the equation now, in which case we're going to get, okay, and then we can use the reduced quadratic formula, which is going to give us, which then gives us, alrighty, and we have our answer. Now the key thing to notice is 11 is greater than the square root of 77, so that means that omega is always going to be negative. So that means that for both of these speeds, omega does spin in the opposite direction, so not the direction shown here, but actually spins in the minus z direction. Okay, now we can actually use this to try and figure out what Q is. So let's go back and substitute for our A. Okay, so we've got A is equal to all of this, and that's equal to minus 11 over omega, and omega is negative. So that means all of this is positive. B was in the positive z direction, and M, the mass, also has to be positive. So according to this logic, I would say that Q has to be positive in this scenario. So once again, I disagree with the solutions. I think that Q has to be greater than 0 in this scenario. Otherwise, this equation can't be true. Alright, and with that, let's have a look at C5. Alrighty guys, so for C5, I'll just do a quick diagram of what our trajectory looks like. Essentially, the ball is going to start somewhere here, and then it's just going to start to spiral outwards, and it's clearly one of the things that we know is that the value for eta, so that's essentially what the angular velocity is not changing with time. So essentially, like our eta dot here is just equal to 1, some constant. And so what that means is that we're going to actually have a cycle go around with a timing of 2 pi. So the period of one cycle is 2 pi in seconds. Now, at this point, I'm just going to say for this part of the problem, we kind of start to leave normal physics a little bit. We just get to throw everything away pretty much. They don't want us to care about units anymore. They don't want us to care about actually using numbers. They've pretty much just set everything to 1. For some weird reason, they've set the moment of inertia to 1 over 11, which is inconsistent with the formula they've given before, but we'll just go with it. And so you can't really dimension check. The other thing to notice is they're telling us that when the number of cycles is very, very large. So essentially this spiral is going to get very, very big. The object is going to be moving very, very fast when it gets far away from the center. The exact initial position you can pretty much ignore, and same for the initial velocity. So what I might just point out that is if the ball is going to get further and further away, but it needs to keep up the same angular velocity, then the velocity is going to get very, very fast. So in this particular case, we can actually pretty much just say that the velocity, so that's r dot or v, is essentially equal to 2 pi times the cycle in our new dimensionless world, so times the cycle number, and in our new dimensionless world, that's also pretty much the radius of the circle. So this one, the velocity is in meters per second, and this one's in meters, but yeah, it doesn't really matter too much. We get to be super casual with units and everything in this part. Alright, so now for the total amount of energy, what they've written looks very complicated, but really this system has got energy. There's 2 types. There's rotational energy and there's the normal kinetic energy. So the rotational energy is equal to I, and then it would be omega squared, except there is a correction term that we're going to have to put into place because we haven't taken into account that the table is spinning. But otherwise it's just the normal I omega squared, and then the kinetic energy is mv squared. Now v is just this 2 pi n, and m is just 1. So this bit here becomes super, super easy to deal with. The only part of this that becomes a little bit complicated is when we want to deal with the fact that the table is actually spinning, then that's going to affect the ball omega, how fast it actually has to rotate. So to take that one into account, what we're going to have to do, we're going to use the no slip condition, and so in the solutions they actually just give us a form of it, which is very convenient, so I'm just going to take it. Omega squared equals v squared plus omega r both squared, plus the cross term. So in this case it's 2 omega v dot z cross r. Now they make a very valid argument in the solutions that once you're very far away from the center, so if you're a long way out on one of these spirals, then essentially v and r are orthogonal to each other. So what that means is that when you take this dot product with this cross product, you're essentially just going to get v multiplied by r. So like this, and then they make note that this can just be factorized like this. Okay, so now and they've told us that they want us to use I equals 1 over 11. So in this expression here, now we've got, okay, and v is just 2 pi n plus omega times r, which is 2 pi n. That's all squared. And then we've still got our second term, so we've still got this term. So plus m equals 1, and v is 2 pi n squared. So if we put all that together, we can factorize out the 4 pi squared n squared. Sorry, I just realized I did a bad thing. You guys are going to get me in a lot of trouble for this. Of course, it's half I omega squared and half mv squared. So all this is multiplied by a half. So this is actually 2 pi squared, not 4 pi squared. Apologies. Alright, and then what I'm going to do here is assume that like everything except for n squared is essentially like a constant now. So we just want to know what's the difference between, so this is like the total energy at the moment. We want to know what's the change in energy from one to the other. So if you like, what's the change in energy? That's if we were going to go from like the nth total energy and subtract off the n minus 1 total energy. So to do that, essentially this is just coming down to subtracting a quadratic. So we have like capital N squared, and we want to essentially subtract off n minus 1 squared from that. So if we do this, our n squared terms are going to cancel out here, and that means that we're just going to get plus 2n and minus 1. Now when n is very large, we can ignore the 1, so this is just going to be equal to 2n. So that means that we just have to double like this expression in here, and so we get 4 pi squared n 1 plus omega over 11 plus 1, this is squared. And that's going to be the change in energy for one cycle. Now the version of the solutions that I've got doesn't have pi squared, it's just got 4, but I believe that that's an error. Alright, and that is a very long and difficult problem over. I hope that you guys have found this helpful. If you found any errors, please let me know and I can update the video. Thank you very much.